Our home galaxy is not as alone as it seems. The Milky Way should be surrounded by a bustling crowd of smaller galaxies, cosmic companions held close by its immense gravity. Yet when we look, we find a puzzling emptiness. Our most trusted theories of the universe predict hundreds of these satellite galaxies, but we can only spot a few dozen. This is not just a small counting error. It is a fundamental crack in our understanding of everything from dark matter to the birth of the cosmos itself. By the end of this journey, you will understand the leading theories that could rewrite the rules of the universe to solve this mystery. We will explore whether our satellites were destroyed, if dark matter is stranger than we thought, or if the universe played a cruel trick during its fiery infancy. The answer forces us to question what we think we know about reality. What does it mean when the map of the cosmos does not match the territory? To find this cosmic crowd, we first need to understand exactly what we are looking for. A satellite galaxy is not just a neighbor floating nearby. It is a prisoner of gravity, a smaller galaxy completely caught in the immense gravitational pull of a giant like our Milky Way. It is forced to orbit just as the Moon orbits the Earth, trapped in a cosmic dance that can last for billions of years. You have likely seen the most famous examples without even knowing it. On a clear, dark night in the southern hemisphere, two faint, hazy patches of light are visible to the naked eye. These are not clouds, they are entire galaxies. The large and small Magellanic Clouds are the Milky Way's most prominent satellites, swirling masses of billions of stars each, forever circling our galactic home. They are the proof that satellite galaxies exist, and they are spectacular. But these two are just the brightest members of what should be a vast entourage. In the grand scheme of the universe, these satellites are the cosmic building blocks, the leftover pieces from the construction of giants like our own galaxy. They are also natural laboratories. Because they are smaller and simpler, they offer a clearer view into the fundamental rules of how galaxies form, and crucially, how the mysterious dark matter that holds them together behaves. By studying these celestial captives, we hope to read the story of our own galaxy's birth. Instead, their puzzling absence has written a mystery. If our most basic cosmic census is so wrong, what else have we misunderstood about the fabric of reality? The universe, according to our best blueprint, should be teeming with these small companions. That blueprint is called the Lambda cold dark matter model, the foundational theory of modern cosmology. It is a set of mathematical rules describing how gravity, dark energy, and dark matter interact to shape everything we see. For decades, it has passed every major test, predicting the large-scale structure of the cosmos with stunning accuracy. To see what this model says about our own galactic neighborhood, scientists feed its equations into the most powerful supercomputers on Earth. These machines simulate the entire universe from a fraction of a second after the Big Bang to the present day, tracing how dark matter clumps together under gravity to form a cosmic web. The results are breathtaking digital universes, and they all tell the same story. In every single simulation, a galaxy with the mass and history of the Milky Way does not evolve in isolation. It forms at the dense knot of a dark matter web, and that web is littered with smaller clumps like droplets clinging to a spider's silk. These clumps are the seeds of satellite galaxies. According to the simulations, our galaxy should be the center of a vast, swirling swarm of at least several hundred, if not thousands, of these small, dark matter-rich satellites. The prediction is not a vague suggestion. It is a specific numerical output repeated across countless supercomputer runs. Now hold that simulated image in your mind, a brilliant central galaxy enveloped by a cloud of faint, orbiting points of light. Then look at the actual map of our skies. The contrast could not be more stark. Where the simulation shows a dense, lively crowd, our telescopes reveal a quiet, almost empty frontier. We see the Magellanic Clouds, a handful of faint dwarf galaxies, and then vast stretches of nothing. It is the difference between expecting a packed stadium and finding only a few scattered spectators in the stands. This is not a minor discrepancy. It is a glaring contradiction between our most successful theory of the universe and the reality we observe outside our window. The satellites are missing, and their absence echoes like a silent alarm in the halls of cosmology. This discrepancy is not a matter of a few dozen galaxies. The numbers are shockingly clear. Our most advanced cosmological simulations consistently predict that a galaxy like the Milky Way should be surrounded by a swarm of several hundred, even thousands, of small satellite galaxies. Yet after decades of searching the skies with increasingly powerful telescopes, astronomers have only definitively catalogued around 60. This is not a minor accounting error. It is a gap so vast it has a name, the missing satellites problem, and it represents one of the most persistent headaches in modern astrophysics. The problem truly came into focus in the late 1990s and early 2000s, a period of explosive progress on two fronts. First, supercomputer simulations of cosmic structure became sophisticated enough to model the formation of individual galaxies and their dark matter halos in stunning detail. For the first time, we had a clear, quantitative prediction of what our galactic neighborhood should look like. At the same time, ambitious new digital sky surveys, like the Sloan Digital Sky Survey, began systematically mapping vast portions of the heavens, revealing thousands of new galaxies but conspicuously failing to find the predicted legions of faint satellites. The two pictures, theory and observation, were placed side by side, and they simply did not match. Imagine building a house using a trusted, detailed blueprint, only to step back and find that half the rooms the blueprint showed are simply not there. The foundation feels solid, the walls are straight, but the structure is incomplete. That is the profound unease this problem introduced. It suggested a major crack in our cosmological foundation, a possibility that something fundamental in our understanding of dark matter, gravity, or the very early universe might be profoundly wrong. Perhaps our telescopes simply were not good enough to see them. This was the most immediate and hopeful explanation for the missing satellites. After all, the models predicted these galaxies would be tiny and faint, composed of just a few thousand stars spread over a vast volume of space. They would be ghosts, their light almost completely washed out by the brilliant glow of the Milky Way's own stars. For decades, our sky surveys were designed to find bright, obvious objects. They were like using a net with wide holes to catch minnows. It was entirely plausible that hundreds of these cosmic minnows were swimming just out of sight, invisible to our coarse instruments. The turning point came with a revolutionary new tool, the Sloan Digital Sky Survey. Instead of relying on photographic plates, it used a massive digital camera and dedicated telescope to systematically scan 1/3 of the entire sky, measuring the brightness and position of hundreds of millions of objects with unprecedented precision. It was like switching from a blurry pair of binoculars to a high-resolution microscope for the heavens. Sloan began to find them, not hundreds but a steady trickle of new, incredibly faint smudges on the edge of detection. These were the ultra-faint dwarf galaxies, each holding only a few hundred to a few thousand ancient stars, yet often embedded in a massive halo of dark matter. They were exactly what the simulations predicted in terms of their faintness, but there were still far fewer than expected. The search accelerated with projects like the Dark Energy Survey, which peered even deeper with more sensitive cameras. Each new survey has added a few more names to the list of known satellites, pulling them from the darkness. Yet, even with these technological leaps, the tally has only climbed to around 60. We have found the faintest galaxies we possibly can with current technology, and the grand total still falls dramatically short of the predicted swarm. This observational hunt has proven two critical things. First, we were indeed missing many satellites because they are incredibly difficult to see. But second, and more importantly, even after accounting for our observational limits, the majority of the predicted satellites are still missing. They are not just hiding in the glare, they are genuinely absent. So if better eyes on the sky have narrowed the gap but cannot close it, the mystery must run deeper than a simple problem of detection. The deficit points to a flaw not in our instruments but potentially in our fundamental assumptions about the universe. Gravity is not just an anchor, it is also a destroyer. Perhaps the satellites are not missing at all, but have been erased from the cosmic record by the very force that bound them to us. This is the tidal disruption hypothesis, a compelling idea that our galaxy's immense gravity acts like a cosmic shredder over billions of years. Imagine a small, fragile cloud of stars drifting too close to a spinning black hole. The side of the cloud nearest the hole feels a much stronger gravitational pull than the far side. This difference in force, a tidal force, stretches and pulls the object apart. Our entire Milky Way galaxy exerts this same tidal pull on anything that comes near it, not from a single black hole, but from the combined gravitational field of its hundreds of billions of stars and its immense halo of dark matter. When a small satellite galaxy ventures into the inner regions of this gravitational well, it does not simply get swallowed whole. It gets stretched and torn into stellar streams, long, ribbon-like filaments of stars that are gradually mixed into the Milky Way's own halo. Dynamic supercomputer simulations show this process in stark, beautiful detail. A dwarf galaxy enters the frame, a cohesive ball of light. As it swings close to the galactic center, invisible tidal forces seize it. It begins to elongate like taffy being pulled, losing its shape entirely. Over successive orbits, it unravels into a faint, shimmering river of stars that eventually disperses, its identity forever lost, its stars assimilated into the larger galaxy. It is a slow, inexorable demolition. The question is whether this galactic digestion can account for the vast discrepancy between the hundreds of satellites predicted and the dozens we see. While tidal destruction undoubtedly happens, and we have observed its ongoing effects in stellar streams like the Sagittarius stream, most cosmologists doubt it is the complete answer. The simulations that predict so many satellites already account for this destructive process. They model the tides, and they still find that a large population of satellites should have survived on more distant, stable orbits, far enough from the galactic center to avoid being shredded. So while the Milky Way's gravity has certainly erased many satellites from the sky, it likely cannot erase the entire problem. The destruction is real, but it is not sufficient. This leads us to a more radical possibility. What if the problem is not with the fate of the satellites, but with their very nature? What if the seeds themselves were different from what we have always assumed? The universe's first light may have been a cosmic culling. To solve the mystery of the missing satellites, we must travel back to the cosmos's infancy, to an era of profound transformation known as reionization. In the first few 100 million years after the Big Bang, the universe was a dark, neutral fog of hydrogen gas. Then the very first stars and galaxies ignited. These pioneers were not like the gentle suns we know today. They were behemoths, monsters that burned hot and fast, flooding the cosmos with a blistering torrent of ultraviolet radiation. This radiation had the power to strip electrons from atoms, to reionize the neutral hydrogen fog that filled all of space. Think of it as a great cosmic sunrise so intense it boiled away a pervasive mist. This epoch of reionization was a fundamental phase change for the entire universe, turning it from opaque to transparent. But for the smallest structures trying to form in that early universe, this first light was not a dawn but a death sentence. The smallest clumps of dark matter, the very seeds that should have grown into our satellite galaxies, were also filled with this primordial hydrogen gas. To form stars, that gas needs to cool down and condense. The intense ultraviolet radiation from those first giant stars and galaxies acted like a universal heat lamp, pouring energy into the gas within these tiny halos. It kept the gas hot, energized, and diffuse, preventing it from ever cooling down and collapsing to spark star formation. The dark matter clump would still exist, held together by gravity, but it would remain barren, a ghostly skeleton of a galaxy with no stars to light it up. These are the true dark galaxies, halos of dark matter and hot gas drifting silently through space, completely invisible to our telescopes which search for starlight. This theory offers an elegant solution. The satellites are not missing. They are all around us, but they are dark. Our predicted hundreds of dark matter halos could indeed be orbiting the Milky Way, just as the simulations foretold. The error was in assuming every one of those halos would inevitably shine. Reionization may have sterilized the smallest, weakest ones, leaving them as permanent shadows in our galactic backyard. If true, it means our census of the cosmos is wildly incomplete. We have been mapping the universe by its lights, while an entire population of invisible dark matter structures moves unseen in the darkness between them. Dark matter may not be what we think it is. For decades, the foundation of our cosmological model has rested on a specific idea called cold dark matter. This version of dark matter is imagined as slow-moving, sluggish particles that clump together easily from the very beginning of the universe. Their slowness allows them to collapse into structures of all sizes, from the tiniest wisp to the largest galaxy cluster. This is why our simulations predict a universe filled with countless small dark matter halos, the seeds for all those missing satellites. But what if dark matter is not cold? What if it is warm? Warm dark matter proposes a different kind of particle, one that is lighter and faster, zipping through the early universe at a significant fraction of the speed of light. This slight shift in properties has a cosmic scale consequence. Those fast-moving particles have too much energy to settle down into the very smallest clumps. They smooth out the universe on small scales, erasing the tiniest seeds before they can ever grow. Imagine trying to build a sandcastle with dry, fine sand. It holds intricate shapes, towers, and tiny details. That is cold dark matter. Now imagine trying to build that same castle with wet, coarse gravel. You can still make a large mound, but all the fine details, the small turrets and delicate walls, are impossible. The gravel simply will not hold that shape. Warm dark matter is that gravel. It still forms the large-scale cosmic web, the massive galaxies and clusters, but it naturally predicts far fewer of the very smallest dark matter clumps. In a warm dark matter universe, the Milky Way would have a smaller, more modest entourage of satellites from the start, neatly aligning with the dozens we observe rather than the hundreds we expected. This is not a minor tweak. It challenges a core pillar of our standard model and connects the vast emptiness of space to the elusive realm of particle physics. The answer to our galactic mystery might not be written in the stars, but in the properties of an invisible particle we have yet to directly touch. Experiments deep underground and in space are now hunting for clues, trying to determine if the dark matter that binds the cosmos is cold, warm, or something stranger still. There is a third, even stranger possibility for the nature of the missing dark matter halos. We have considered dark matter that is cold and clumpy, and dark matter that is warm and smooth. But what if dark matter is not just a ghostly presence, but a ghost that can touch itself? This idea is called self-interacting dark matter, and it proposes that these invisible particles do not just ignore normal matter. They occasionally interact with each other through a new, unknown force. It is a subtle but profound shift. In our standard model, dark matter particles pass right through each other like ships in an endless, silent night. They feel only gravity, which pulls them together into dense, cuspy cores at the center of their halos. But if dark matter particles can bump into one another, if they experience a kind of cosmic friction, everything changes inside those small satellite halos. When particles collide, they transfer energy, much like billiard balls scattering on a table. This energy transfer has a smoothing effect. It prevents the dark matter from piling up into an extremely dense, sharp peak at the halo's center. Instead of a steep cusp, self-interactions create a gentle, fluffy core. Think of it like the difference between a hard, compact snowball and a soft, loosely packed snowdrift. This fluffiness matters enormously for star formation. A dense, cuspy dark matter core creates a deep, steep gravitational well, a powerful trap that can effectively pull in cooling gas and compress it until stars ignite. But a soft, diffuse core creates a much shallower well. Its gravitational pull is weaker and more spread out. For a small halo trying to form its first stars in the hostile era of reionization, this is a death sentence. The hot gas, already struggling to cool under the ultraviolet glare, now faces a weaker gravitational anchor. It is far less likely to condense and collapse. The halo remains a dark galaxy, a ghost of dark matter with no stars to call its own. So, like the warm dark matter scenario, self-interacting dark matter offers a pathway to a universe where the predicted multitude of dark matter halos exists but remains invisible. The satellites are there, orbiting silently, not because their seeds were erased, but because their internal structure was softened, rendering them stillborn. This concept pushes our imagination to its limits, asking us to conceive of an entire shadow universe of particles with their own hidden forces and interactions, a parallel physics whose only signature might be the haunting emptiness where we expected to see a crowd of stars. The invisible forces of dark matter may have shaped the stage, but the visible actors, the stars and gas we can see, played a decisive role in this cosmic drama. For a long time, our simulations treated normal matter, the protons and neutrons that make up stars and planets, as a passive passenger in dark matter's gravitational grip. But normal matter, or baryonic matter, has a voice of its own, and in the early universe it screamed. Within the first generations of galaxies, titanic events were unfolding. Massive stars, living fast and dying young, ended their lives in catastrophic supernova explosions. At the centers of larger galaxies, gas spiraling into supermassive black holes ignited as brilliant, violent beacons called active galactic nuclei. Both of these processes unleash unimaginable energy, not as gentle light, but as raging winds and shockwaves that slam into the surrounding gas. In a large galaxy, this fury is contained by a deep gravitational well. But in a tiny, fledgling satellite halo, the gravitational hold is tenuous, like a child trying to hold onto a balloon in a hurricane. The energy from even a single supernova or the distant blast from a neighboring active galaxy can be enough to blow all the star-forming gas clean out of the small halo. The gas is heated, accelerated, and ejected into intergalactic space, a process astronomers call feedback. A halo stripped of its gas is a galaxy that can never grow. It is left a dark matter skeleton, a celestial fossil that will never shine. For decades, our cosmological simulations were too simple to capture this intricate, violent ballet of baryonic physics. They could model dark matter's gravity with exquisite detail, but the complex, explosive feedback from stars and black holes was a missing ingredient. We were simulating a universe without its own most powerful engines of change. The latest generation of supercomputer simulations with names like Fire and Illustris TNG are changing the game. They are now sophisticated enough to incorporate these feedback mechanisms, modeling not just gravity, but the actual birth, life, and explosive death of stars within the evolving cosmic web. The results are transformative. In these new, more realistic virtual universes, the frenetic energy of the early cosmos does not just blow on a few halos, it sweeps through the population of the smallest structures like a cosmic scythe. Vast numbers of the tiniest dark matter clumps have their gas reservoirs scoured away before they can form more than a handful of stars, if any at all. They become exactly the kind of ultra-faint or completely dark satellites we struggle to find. When scientists run these advanced simulations and then apply the same observational limits our telescopes face, something remarkable happens. The predicted number of visible satellites around a Milky Way-like galaxy begins to drop, falling much closer to the 60 or so we actually observe. The gap between theory and reality starts to close, not by changing the rules of dark matter, but by finally giving normal matter its due. This suggests a profound and humbling possibility. The missing satellites problem may not be a sign of a broken cosmological model, but a sign of our own previous ignorance. We were missing a key piece of the story because we underestimated the sheer transformative power of the stars themselves. But the plot thickens with an even thornier puzzle. Even the satellites we have managed to find, the few dozen faint dwarfs orbiting our galaxy, are themselves a source of deep confusion. This is called the too big to fail problem, and in many ways it is a more serious challenge than simply counting missing galaxies. Our most sophisticated simulations do not just predict a vast number of small dark matter clumps, they also predict their internal structure, their density. And according to those simulations, the most massive of these predicted subhalos, the ones just below the size of the Magellanic Clouds, should be incredibly dense fortresses of dark matter. Their gravitational pull would be so strong that if they hosted a galaxy, that galaxy would be forced to form a huge number of stars. It would be bright, massive, and utterly impossible to miss. In the simulations, these are the giants among satellites, the ones too big to fail at forming prominent, star-filled galaxies. Yet when we look at the actual, real-world satellites of that predicted size and mass, we see something completely different. The largest dwarf galaxies we observe, like Fornax or Sculptor, are far dimmer and far less massive in stars than they should be if they lived inside those predicted dense halos. It is as if the simulation says the universe should have built towering, gleaming skyscrapers, but when we go to the address, we find only modest, single-story houses sitting on foundations meant for giants. This discrepancy is devastating because it attacks the survivors. The first problem asked why we do not see hundreds of faint galaxies. We could explain that away by saying the smallest ones never lit up. But the too big to fail problem asks why the biggest, most successful satellites we do see are themselves cosmic underachievers. Their very existence in their observed faint and puffy state contradicts the detailed predictions of what a dark matter halo of that mass should look like. It suggests an error not just in the number of halos, but in their very internal architecture. Solving this requires more than hiding galaxies. It demands fundamentally reshaping the dark matter cores we thought we understood. Our galaxy's serene spiral arms hide a violent past. We often picture the Milky Way as a stable, isolated island in space, but new data paints a far more dynamic and brutal history, one that could hold a key to the satellite mystery. The revolutionary Gaia Space Observatory, meticulously mapping the positions and motions of over 1 billion stars, has uncovered ghostly evidence of ancient collisions. It has revealed that our galaxy did not form in quiet isolation but grew through a series of colossal mergers, cannibalizing smaller galaxies that ventured too close. The stars from those devoured galaxies were not completely assimilated. They were strewn across the Milky Way's halo, leaving behind faint, flowing rivers of stars called stellar streams. These streams are the archaeological remains of past galactic meals, and they tell a story of chaos. The most dramatic of these events is nicknamed the Gaia Sausage, the remnants of a massive dwarf galaxy that slammed into the young Milky Way around 10 billion years ago. This was not a gentle merger. It was a head-on, catastrophic collision that likely shook the entire galactic foundation, sending shockwaves through the dark matter halo and everything orbiting within it. Computer animations of this event show a smaller galaxy plunging directly into the heart of the Milky Way, its stars torn into a spray that forms a distinct sausage-shaped distribution in motion space, a fossilized imprint of the impact. The energy from such a monumental crash would have been apocalyptic for any smaller satellites caught in the turmoil. Imagine a calm pond with many small leaves floating on the surface. Now throw a large rock into the center. The resulting waves would not just ripple outward, they would violently jostle, sink, or scatter many of those leaves. In galactic terms, the gravitational shockwaves from the Gaia-Sausage merger could have done exactly that to the Milky Way's early satellite population. Orbits would have been radically destabilized. Many small satellites might have been flung out into intergalactic space entirely, ejected from the Milky Way's grasp. Others could have been dragged inward on doomed trajectories, hastening their tidal destruction. This violent chapter in our galaxy's biography suggests a compelling possibility. Perhaps the swarm of satellites predicted by the pristine simulations never had a chance to fully form or survive. Our galactic neighborhood was not a quiet nursery, it was a demolition derby. The missing satellites might not be missing from the universe, but simply missing from our immediate vicinity, scattered to the cosmic winds by the gravitational aftershocks of our own violent youth. This idea forces us to see our home not as a passive backdrop, but as an active, shaping force in the mystery. The emptiness we observe today may be the lasting echo of a colossal crash from the deep past. These faint, ghostly satellites are more than just a mystery to be solved. They are the universe's own dark matter detectors, offering us a direct window into the invisible architecture of reality. Every ultra-faint dwarf we discover, with its sparse sprinkling of ancient stars, holds a profound secret. When astronomers measure the motions of those few stars, they reveal something astonishing. The stars are moving far too quickly for the feeble gravitational pull of their own visible mass to hold them together. They should be flying apart, yet they remain bound in a coherent galaxy. The only explanation is that they are embedded in an immense, crushing sphere of unseen matter, a dense halo of dark matter that provides the gravitational glue. This gives each satellite an extreme mass-to-light ratio. For the faintest dwarfs, this ratio can be over 1,000 to 1, meaning for every bit of mass we see in starlight, there are 1,000 times more mass in the form of dark matter holding it all together. They are not just galaxies with some dark matter. They are essentially dark matter halos that happen to have a handful of stars trapped inside, like fireflies caught in a massive, invisible bottle. By meticulously tracking the orbits and velocities of these fireflies, the individual stars within a dwarf, astronomers can perform a kind of cosmic forensics. The speed and direction of each star act as a tracer, mapping the shape and strength of the invisible gravitational field that confines them. This technique, called kinematic modeling, allows us to chart the density and distribution of dark matter within these halos with a precision that no earthbound laboratory can match. We are literally using starlight to draw a map of the invisible, but the potential goes even deeper. If dark matter particles are not completely inert, if they can interact with one another and annihilate upon collision, as some leading theories suggest, then the dense cores of these satellite galaxies could be the perfect place to look for the aftermath. When two dark matter particles annihilate, they are theorized to convert into a burst of standard particles, including high-energy gamma rays. The centers of these dark matter-dominated dwarfs, where the particles are most densely packed, would be the brightest expected sources of this elusive signal in the entire sky. For over a decade, instruments like the Fermi Gamma Ray Space Telescope have been staring at these ultra-faint satellites, searching for any faint, unexplained excess of gamma rays emanating from their hearts. A definitive detection would be a monumental breakthrough, finally revealing the particle identity of dark matter. So far, the search has come up empty, placing critical limits on what dark matter can be. Yet every new, faint satellite discovered adds another target, another natural experiment to the portfolio. In this way, the missing satellites problem has transformed into an incredible opportunity. Each dim smudge of light on the edge of detection is not just a puzzle piece in a galactic census. It is a potential lighthouse built by the universe itself, possibly signaling to us from the dark shore of a hidden reality. This cosmic detective story is about to receive its most powerful tool yet. In the remote, dry air of the Chilean Andes, a new eye on the universe is preparing to open. The Vera C. Rubin Observatory, with its groundbreaking 8.4-meter mirror and a camera the size of a small car, is not just another telescope. It is a time machine and a census taker designed to execute the legacy survey of space and time. For 10 years, it will scan the entire southern sky over and over, creating the deepest, widest cinematic portrait of the universe ever made. Its mission will transform our view of the dynamic cosmos, but for the mystery of the missing satellites, it promises nothing short of a revolution. The key is in the survey's staggering depth and precision. Where current telescopes see only the brightest few dozen satellite galaxies, the Rubin Observatory's LSST will peer into the deepest shadows of our galactic halo. It is built to detect the faintest, most diffuse smudges of starlight imaginable, the ghosts of galaxies that have, until now, remained perfectly camouflaged against the black velvet of space. Astronomers running simulations with the LSST expected capabilities arrive at a staggering conclusion. Instead of a few dozen known satellites, we are likely to discover thousands. Not dozens, but thousands of new ultra-faint dwarf galaxies and stellar streams orbiting the Milky Way and our neighboring galaxy, Andromeda. This will not just add to our list, it will give us, for the very first time, a complete and statistically robust population to study. We will move from guessing in the dark to analyzing a vast celestial database. Each newly discovered satellite is another data point, another clue. Their exact numbers, their distributions across the sky, their shapes, and their motions will form a definitive test for every competing theory. Do we see a smooth distribution of dark, star-poor halos, suggesting reionization sterilized them? Does the population structure hint at the warm, smoothing effect of fast-moving dark matter particles? Or does the pattern of orbits bear the unmistakable scars of ancient galactic collisions, like the Gaia sausage? The LSST will provide the evidence to convict or exonerate these cosmic suspects. It turns a philosophical debate into a quantitative science. We stand on the brink of a flood of discovery that will either confirm our standard model of cosmology by finally revealing the hidden satellites it predicted, or it will deliver the precise, overwhelming data needed to dismantle it and build something new. The answer is written in faint starlight, and we are finally building the instrument that can read it. This cosmic census problem does not end at the Milky Way's edge. Our closest galactic neighbor, the magnificent Andromeda Galaxy, holds up a mirror to our own mystery. Lying 2.5 million light-years away, Andromeda is a near twin of the Milky Way, a similar spiral giant with a similar gravitational pull. If our missing satellites were due to some unique, violent history like the Gaia sausage merger, then Andromeda, with its own independent past, might show a completely different result. Its satellite population could be rich and full, highlighting our own galaxy's peculiar emptiness. That is not what astronomers see. Detailed surveys of Andromeda's halo, most notably the Pan-Andromeda Archaeological Survey, have meticulously mapped its satellite system. The result is both confirming and puzzling. Andromeda also has far fewer bright satellite galaxies than the simplest dark matter simulations predict. The discrepancy is there, clear as day. This universalizes the problem in a profound way. It is not just about our galactic backyard. It is a fundamental feature of how giant spiral galaxies form within the cosmic web of dark matter. Two independent galaxies with different formation histories and different environments, both exhibit the same puzzling lack of small companions. This coincidence is too significant to ignore. It tells us we are not studying a local anomaly or a quirk of the Milky Way's violent youth. We are observing a universal rule, a hidden piece of physics that operates everywhere, shaping all galaxies of a certain size. The solution, therefore, must be equally universal. Whether it is the sterilizing effect of reionization, the smoothing nature of warm dark matter, or the transformative power of stellar feedback, the answer must apply to Andromeda just as it applies to us. This transforms the missing satellites from a curious puzzle into a cornerstone of modern cosmology. Cracking this code is not about fixing a single error in our galactic map. It is about rewriting the instruction manual for how structure forms across the entire universe. Every great scientific model is a story we tell about the universe, and like all stories, it is tested at its edges. The Lambda cold dark matter model is the most successful cosmological narrative ever written, a framework that explains the large-scale structure of everything we see. Yet the missing satellites are a whisper from the fringe, a persistent detail that does not quite fit the plot. If this whisper grows into a shout, if we confirm that the simplest version of our story is fundamentally wrong, the implications ripple far beyond a galactic headcount. It would mean that our universe operates by rules we have not yet imagined. Science does not progress in a straight line of accumulating facts. It advances through a dynamic tension, a sometimes uncomfortable push and pull between the elegant predictions of our theories and the messy, contradictory data from the real world. A theory makes a bold claim about how nature should behave. An observation, like the puzzling lack of satellites, stands up and says, but it does not. This is not a failure of science, it is the engine of science. It is the moment of maximum creative potential. For decades, our standard model of cosmology has been remarkably resilient, absorbing new data with minor adjustments. But the missing satellites, coupled with the too big to fail problem, represent a strain that cannot be ignored forever. They are a crack in the foundation, and through that crack, we might glimpse an entirely new layer of reality. Solving this mystery would not merely fill a gap in a galactic catalogue. It could force a paradigm shift, a fundamental change in our understanding of the cosmos's basic ingredients and governing laws. We have been here before. In the late 1990s, astronomers observing distant supernova made a shocking discovery. The expansion of the universe was not slowing down due to gravity, as everyone expected. It was accelerating, pushed apart by a mysterious repulsive force we now call dark energy. That single observation did not just add a new chapter to the old story. It demanded a rewrite of the entire book, introducing a dominant, unknown component that shapes the fate of the cosmos. The discovery of dark energy was a monumental paradigm shift, born from the tension between prediction and observation. The missing satellites problem carries that same transformative energy. It is a similar anomaly, a stubborn piece of data that refuses to conform. Its resolution could be just as profound. Will we discover that dark matter is not a single, simple particle, but a rich spectrum with its own hidden forces and interactions? Will we learn that the early universe was a far more violent and transformative place than our simulations can capture? Or will we uncover a subtle flaw in our understanding of gravity itself on galactic scales? Each possibility points toward a new cosmological paradigm, a universe that is stranger, more dynamic, and more intricate than our current story allows. The quiet emptiness around our galaxy is not an absence of information. It is a question written in the negative space of the cosmos, and the answer will redefine our place within it. The hunt for invisible galaxies demands tools that can see the unseen. This cosmic search has become a proving ground for some of the most advanced computational techniques on the planet, pushing the very limits of artificial intelligence. Modern sky surveys like the one the Vera see, Rubin Observatory will conduct do not just collect pretty pictures. They generate a fire hose of data, a torrent of petabytes containing the positions, colors, and shapes of billions upon billions of celestial objects. Finding a handful of ultra-faint satellites in this digital ocean is the proverbial search for a needle in a haystack, if the needle were made of the same translucent material as the hay and constantly moving. Human eyes and traditional software are utterly overwhelmed by this scale. The solution has been to train a new kind of digital detective, machine learning algorithms that can learn the subtle signature of a dwarf galaxy. Scientists feed these algorithms thousands of examples, both simulated satellite galaxies and known contaminants like distant star clusters or messy clumps of foreground stars. The AI learns to distinguish the real, diffuse smudge of a distant dwarf from the noise, recognizing patterns and shapes too faint and complex for any human to reliably pick out. It is a process of teaching a computer to have a kind of cosmic intuition. These algorithms do not just look, they sift and score, assigning a probability that any given faint patch of pixels is a genuine galaxy. This has already led to the discovery of new, incredibly faint satellites in existing data, candidates that human scanners had missed for years. The AI acts as a force multiplier for human curiosity, scanning decades of observations in days and highlighting the most promising targets for our telescopes. But the impact of this technological push ripples far beyond the dome of an observatory. The machine learning frameworks developed to find ghostly galaxies are now being adapted to solve problems here on Earth. The same pattern recognition prowess used to spot a diffuse cluster of stars can be trained to identify early signs of disease in medical scans, picking out the faint, irregular shapes of tumors that might escape a radiologist's first glance. The data processing pipelines built to clean cosmic images of interference are being used to enhance satellite imagery of our own planet, monitoring deforestation, tracking urban growth, or spotting environmental changes with unprecedented clarity. The algorithms that model the gravitational dance of dark matter are cousins to those that predict complex systems like global weather patterns or financial markets. In a very real sense, the drive to solve a deep space mystery is refining a set of powerful, universal tools. We are building artificial minds to comprehend the cosmos, and in doing so, we are giving them the vision to better understand our own world. The search for the missing satellites is quietly accelerating a technological revolution, one intelligent scan at a time. The ultimate prize in this cosmic hunt is a true dark galaxy, a structure built entirely from dark matter with not a single star to give it away. We have strong candidates, these ultra-faint dwarfs dominated by unseen mass, but the Holy Grail is a halo that never managed to spark any stellar fire at all. Finding one would be the most direct proof that our ideas about reionization or feedback are correct, and it would give us a pristine laboratory to study dark matter alone, free from the complicating glare of stars. So how do you find something defined by its absence of light? Astronomers have turned to two ingenious methods, listening for whispers and watching for bends in reality itself. The first technique involves not optical telescopes, but massive radio dishes tuned to a specific quiet song of the cosmos. Neutral hydrogen gas, the raw fuel for stars, emits a faint radio signal at a wavelength of 21 centimeters. This signal is a beacon, and it can be detected even if the gas itself is cold and not forming stars. Projects like the Arecibo Legacy Fast LF survey, and now the powerful square-kilometer array pathfinders scan the skies not for starlight but for these ethereal clouds of hydrogen. They have found many strange, free-floating clouds, some with masses akin to small galaxies but no visible stars. These could be the ghosts we are looking for, dark matter halos that retained their gas but never ignited. The challenge is proving these clouds are truly bound by dark matter and not just tidal debris from a past galactic collision. The second method is even more subtle, relying on a prediction from Einstein's theory of general relativity. Massive objects like a dense clump of dark matter warp the fabric of space-time around them. When light from a distant background galaxy passes through this warped region, its path is bent and distorted, a phenomenon called gravitational lensing. It is like looking through the bottom of a wine glass at a distant streetlight. The image stretches and curves. By meticulously analyzing the shapes of millions of distant galaxies, astronomers can map the invisible mass distorting their light, revealing dark matter clumps even if they contain no stars, no gas, nothing but pure gravitational influence. A definitive detection through lensing would be a smoking gun. Imagine mapping the silhouette of an invisible giant solely by the way it bends the light streaming past it. Discovering a true dark galaxy through either method would be a landmark moment. It would validate the idea that the universe is filled with these invisible structures, solving the missing satellites problem not by changing the rules of dark matter, but by finally seeing the dark population we always knew must be there. It would confirm that our cosmic census was not wrong, just tragically incomplete, forever limited by our dependence on light. But what if the very premise of our search is wrong? For decades, we have chased invisible particles to explain the missing satellites, operating on a core assumption that our theory of gravity, Einstein's general relativity, is complete and correct on all scales. A small but vocal group of physicists challenges that assumption at its root. They propose a radical alternative, a theory that requires no dark matter at all. It is called modified Newtonian dynamics, or MUND. Its central idea is deceptively simple. Perhaps gravity does not behave exactly as Newton or Einstein described when it becomes incredibly weak, such as in the outer reaches of galaxies or in the vast, sparse spaces between them. MUND suggests that below a certain, extremely low acceleration threshold, the force of gravity strengthens slightly compared to the standard predictions. This tiny modification, its proponents argue, is enough to explain why stars at the edges of spiral galaxies orbit too quickly, why galaxy clusters seem to hold more mass than we see, and crucially for our mystery, why large galaxies like ours have so few satellites. In the MUND framework, the gravitational glue holding galaxies together is not an invisible halo of exotic particles. It is gravity itself, acting with a slightly different set of rules in the faintest realms of the cosmos. This leads to a very different prediction for satellite populations. Under standard dark matter theory, small halos form abundantly. Under MUND, the conditions to spawn a self-gravitating satellite are much rarer and more fragile. The theory naturally predicts that giant spiral galaxies should have only a modest number of companions, much closer to the dozens we observe rather than the hundreds predicted by cold dark matter. MUND advocates the missing satellites are not a problem to be solved with new particles, but a direct confirmation that our map of gravity itself needs revision. This is a profound philosophical split. It is the difference between inventing a new, unseen substance to fill a gap in our equations versus rewriting the equations themselves. While the majority of the cosmology community finds more evidence for the dark matter paradigm, MUND remains a persistent and important minority viewpoint. Its existence is a testament to the health of scientific debate at the absolute frontier. When faced with a deep cosmic puzzle, we must rigorously test every logical path, even those that lead us to question our most fundamental laws. The continued challenge from theories like MUND ensures that the dark matter hypothesis is not accepted simply because it is popular, but because it survives a relentless gauntlet of tests and explains a wider universe of data. This tension is not a weakness of cosmology, but its greatest strength. It means the mystery of the missing satellites is so compelling, so fundamental, that it forces us to consider every possibility, from hidden particles to rewritten laws of physics, in our quest to understand the true nature of the cosmos. While dark matter and stellar explosions shaped the cosmic landscape, another invisible force was at work in the early fog. We often forget that the universe is not just a collection of matter and gravity, it is also threaded with magnetism. The origin of cosmic magnetic fields is a mystery in itself, but many scientists believe weak, primordial fields were woven into the fabric of space from its earliest moments. These fields, incredibly diffuse at first, were stretched and amplified by the motions of gas during the formation of the first structures. At the same time, the first generations of massive stars, in their violent supernova deaths, did more than blast gas away. They accelerated protons and atomic nuclei to nearly the speed of light, creating a pervasive bath of high-energy cosmic rays. This combination, magnetic fields and cosmic rays, introduced a subtle but powerful new physics into the small, vulnerable halos that were trying to form the first satellite galaxies. To understand their effect, think of a pot of water on a stove. For the water to boil, heat must escape from the liquid, allowing it to transition to steam. In a similar way, for a cloud of primordial gas to collapse and form stars, it must be able to cool down. It does this by radiating away its thermal energy, like a hot piece of metal glowing as it cools. In the simplest early universe, the main coolant was hydrogen gas, which radiates energy efficiently when it gets dense. But magnetic fields and cosmic rays change this cooling process in profound ways. Magnetic fields, even weak ones, can channel the motion of charged particles and influence how heat is transported through a gas cloud. More importantly, cosmic rays are relentless. These high-energy particles constantly bombard the gas within a small halo, depositing energy like microscopic bullets. This bombardment acts as a persistent heating source, counteracting the gas's attempts to cool and condense. For a massive galaxy with a deep gravitational well, this extra heat is a minor nuisance, easily overcome by the powerful pull of gravity. But for a tiny proto-satellite halo with a gravitational grip as delicate as a whisper, this extra energy can be the difference between life and death. The cosmic rays keep the gas just warm enough, just puffed up enough, that it never reaches the critical density needed for the first star to ignite. It is like trying to light a campfire in a gentle but constant drizzle. The wood may be dry enough in theory, but the persistent moisture prevents the flame from ever taking hold. This introduces another layer of feedback, but not from within the galaxy itself. It is an environmental feedback, a background condition of the early cosmos that could have selectively stifled the smallest structures. When scientists incorporate these complex physics into the latest supercomputer simulations, the results are striking. The models show that primordial magnetic fields can indeed slow down the collapse of gas in small halos. The cosmic ray background further heats the tenuous gas, making it even more resistant to falling into the shallow gravitational wells of the smallest dark matter clumps. This does not necessarily erase the halos, but it can dramatically delay or even permanently suppress star formation within them. It provides yet another mechanism for creating the population of dark galaxies that our telescopes cannot see. This research is on the cutting edge, reminding us that the early universe was not a simple, quiet place. It was a dynamic and multifaceted arena where gravity, radiation, magnetic forces, and high-energy particles were all in a constant, complex dance. The fact that any small galaxies formed at all is a testament to the overwhelming power of gravity in the right conditions, but for the smallest seeds the conditions were rarely right. They were buffeted by ultraviolet light from reionization, blasted by winds from their larger neighbors, and gently but persistently warmed by a sea of cosmic rays threaded with magnetic fields. It is a wonder we see any ultra-faint dwarfs at all. Each one that survived is a cosmic champion, a tiny overcomer that managed to form stars against a universe seemingly designed to keep it dark. Our galactic story expands beyond our own halo into a community of giants. Picture the local group not as a random scattering of islands, but as a vast, slow-motion arena where two superpowers, the Milky Way and Andromeda, dominate the gravitational landscape. Each is a colossal spiral galaxy, a titan surrounded by its own court of dwarf satellite galaxies, all bound together in a delicate billion-year dance. Their immense gravity does not just hold their own satellites, it creates a sphere of influence, a zone where they can steal from one another or fling objects into the void. The future of every small galaxy in our neighborhood is written in the slow, inevitable pull between these two rulers, and that future holds a cataclysm. In roughly 4.5 billion years, the Milky Way and Andromeda are destined to collide. This is not speculation, it is a forecast written in the precise motions measured by telescopes like Gaia. They are moving toward each other at a terrifying speed of about 110 kilometers per second. The collision will not be a sudden, explosive crash, but a drawn-out, majestic merger. For billions of years, the two galaxies will swing past each other, their gravitational forces whipping like tidal tsunamis through their satellite systems. It will be a period of cosmic chaos. Satellites on stable orbits will be violently perturbed. Some will be flung outward on long, lonely trajectories into intergalactic space, forever lost to either giant. Others will be hurled inward, accelerated toward the chaotic centers of the merging galaxies to be torn apart more quickly. The delicate populations we see today, the few dozen dwarfs around each giant, will be scrambled, redistributed, and decimated. This impending merger reframes the missing satellites problem on an epic temporal scale. We are looking at a snapshot, a single frame in a multi-billion-year film. The quiet frontier we see today might be a momentary lull, a calm before a storm that has already begun in the grand scheme of cosmic time. Perhaps our galaxy once had more satellites, but Andromeda's looming gravity has already begun to strip them away over the eons, a slow theft happening just below our threshold of detection. Or perhaps after the merger is complete and a new giant elliptical galaxy, Milky Way, rises from the chaos, the satellite population will be even more depleted, the result of a galactic consolidation that erases the smallest entities. This narrative transforms the satellites from static puzzle pieces into a dynamic, migrating population caught between two approaching giants. Their fates are intertwined with a destiny written 4.5 billion years ago. The emptiness we puzzle over today might simply be the opening act of a much larger, slower, and more violent story of galactic empire and conquest. This grand mystery is not reserved for astronomers with giant telescopes. The search for the missing satellites has opened a door for anyone with curiosity and an internet connection. Across the globe, a quiet revolution in discovery is underway, powered not by multi-million-dollar instruments, but by the collective curiosity of everyday people. Projects like Galaxies Zoo and Hubble Asteroid Hunter invite the public to become active partners in cosmic exploration. The premise is beautifully simple. Supercomputers and telescopes generate mountains of image data, far more than any professional team could ever analyze on their own. These projects present this raw data online, offering quick tutorials and straightforward tasks. In Galaxy Zoo, you might be asked to classify the shapes of distant galaxies, helping to map the universe's structure. In Hubble Asteroid Hunter, you scan archival images for the faint streaks left by unknown asteroids. The human brain, with its unparalleled pattern recognition, can spot subtle anomalies and complex shapes that even the most advanced algorithms can still miss. This is citizen science, and its impact is profound. Volunteers have discovered entirely new classes of galaxies, identified gravitational lenses, and found thousands of asteroids. They are doing the essential, meticulous work of sifting cosmic sand to find gold dust. This model is perfectly suited for the next phase of the satellite hunt. When the Rubin Observatory begins its decade-long survey, it will produce an unprecedented avalanche of data, capturing the entire southern sky every few nights. Within that torrent of pixels will be the faint, moving smudges of countless new ultra-faint dwarf galaxies and stellar streams. While machine learning will flag many candidates, the keen eye and intuition of a human volunteer could be the key to spotting something truly strange, something the algorithm was not trained to see. The next faint satellite of the Milky Way, or even a completely dark galaxy revealed by its gravitational lensing effect, might well be first identified by a teacher, a student, or an enthusiast at home clicking through images after dinner. This transforms the scientific journey from a distant spectacle into a shared endeavor. You are not just learning about the mystery, you can join the search. The answer to what shapes our galactic neighborhood may ultimately be found through a collaboration between the most powerful telescope ever built and the innate curiosity of people everywhere, proving that the cosmos still holds secrets for anyone willing to look. These virtual universes are now laboratories of staggering complexity. The latest generation of supercomputer simulations with names like Illustris TNG and FIRE2 are not just tracing dark matter. They are building synthetic galaxies from the ground up, modeling the chaotic physics of star formation, the explosive deaths of supernova, the blistering radiation from newborn stars, and the voracious energy of supermassive black holes. It is a symphony of cosmic forces, each note calculated with unprecedented precision. The goal is not just to predict where dark matter clumps, but to see which of those clumps actually light up with stars we could observe. These simulations are the ultimate test for our theories, a controlled environment where we can run the universe's rules forward and see what emerges. And what emerges is both promising and perplexing. When these high-resolution models account for the full fury of stellar feedback, the number of bright, visible satellites around a Milky Way-like galaxy drops dramatically. The violent winds from supernova and young stars effectively blow the gas out of the smallest halos, leaving them dark or, at best, seeding them with only a handful of ancient stars. This brings the simulated satellite count much closer to the dozens we actually see. For the first time, theory and observation are beginning to whisper in agreement. Yet tensions stubbornly persist. While these advanced simulations can produce the right number of faint satellites, they often struggle to replicate the exact internal properties of the ones we find. The simulated dwarf galaxies might still be too centrally concentrated, or their stars might not have the exact chemical signatures we measure in real objects like the Sculptor or Fornax dwarfs. It is as if we have finally built a clock that tells the correct hour, but its minute hand still twitches in the wrong direction. These lingering discrepancies are not failures, they are priceless clues. They tell scientists that a crucial ingredient is still missing from the recipe, perhaps the subtle effects of cosmic rays or the intricate dance of magnetic fields in the early gas. Every mismatch is a signpost driving a new cycle of innovation. Researchers are now pushing the simulations further, increasing resolution to see finer details or adding entirely new layers of physics. The quest to solve the missing satellites is in essence a race to build a perfect digital universe, one whose predictions match our reality down to the faintest smudge of light in the sky. The cosmos keeps its deepest secrets for those who dare to ask the next question. If you are watching this and feel that pull of curiosity, if the idea of an invisible universe makes your mind race, then this message is for you. The mystery of the missing satellites is not a closed case. It is a wide-open frontier, a puzzle that will likely be solved by someone who is right now just beginning their journey. This will be a defining challenge for the next generation of astrophysicists, and the tools you will need are being forged today. You will not just peer through telescopes. You will write the code that builds virtual universes in supercomputers, crafting simulations of such complexity they blur the line between digital art and scientific prophecy. You will master data science, sifting through petabytes of sky survey images with machine learning algorithms you helped design, training artificial intelligence to see the ghosts we cannot. You will wrestle with theoretical physics, probing the fundamental nature of dark matter and gravity, perhaps rewriting the equations that describe reality itself. This is not a solitary pursuit in an ivory tower. It is a global, collaborative detective story. You might find yourself writing software one day, analyzing the chemical fingerprints of ancient stars the next, and presenting a discovery to the world the day after that. The path requires patience and creativity in equal measure. You will stare at screens filled with numbers that tell the story of a faint smudge of light 200,000 light years away. You will learn to speak the language of mathematics to describe the indescribable, and you will need to embrace the unknown, for the answer may not be a simple missing piece, but a whole new board on which the game is played. The universe has posed a brilliant, stubborn riddle. It is waiting for you to find the answer. From a puzzling mismatch to a profound cosmic mystery, our journey has traced the edges of what we know. We began with a simple but shocking fact: a galaxy like ours should be swarming with hundreds of small companions, yet our telescopes find only a few dozen. That emptiness launched us into a detective story spanning the entire history of the universe. We explored how the first starlight might have sterilized the smallest galaxies, leaving them dark and invisible. We questioned the very nature of dark matter, wondering if it is warm and smooth rather than cold and clumpy, or if its particles interact in hidden ways that prevent stars from ever igniting. We gave voice to the explosive power of normal matter, to supernova and black holes whose furious winds could have scoured gas from fragile halos. We even looked to our galaxy's own violent past, to colossal mergers that might have scattered a primordial crowd to the cosmic winds. Each theory is a different path through the same dark forest, an attempt to explain the quiet frontier around our galactic home. This is not an academic exercise. Solving the missing satellites problem will force us to refine the fundamental recipe of the cosmos itself. Is dark matter a simple particle or a complex spectrum with its own hidden physics? Did the earliest stars and galaxies wield more transformative power than we ever dreamed? The answer will rewrite a chapter in the instruction manual of the universe. So the next time you find yourself under a clear, dark sky, look up. That majestic band of the Milky Way is not just a beautiful sight. It is the center of a great mystery, surrounded by ghosts we are only learning to see. The final clues are now falling into place, pixel by pixel, in the data streams from new eyes on the cosmos like the Vera C. Rubin Observatory. The story of our galactic neighborhood and of the universe's hidden architecture is being written right now. Stay curious and follow where the light leads.